Welcome to Pratidhwani, where we try to humanize science. I'm your host, G.V. Pawan Kumar. Before I introduce you to my guest, let me thank all the listeners for their excellent response. As you know, Pratidhwani is a non-commercial podcast, and I run this in my individual capacity. So your feedback is important for us to improve the production. So please share your views and thoughts. I'm on Twitter and Facebook, and I'll be glad to interact with you. Now to the interesting part. In this episode, I'm delighted to introduce you to my guest, Seema Sharma. Seema is an experimental particle physicist who was also part of the experimental discovery of Higgs Boson at CERN, Geneva. She is an associate professor in the Department of Physics at the Indian Institute of Science, Education and Research, Pune, and is also an experimental collaborator at Large Hadron Collider at CERN, Geneva, which is one of the largest, if not the largest, experimental physics laboratory in the world. She also holds the leadership position of deputy spokesperson of India CMS collaboration, which essentially comprises of 15 universities and institutions across the country. In this episode, we discussed about her journey from Rajsamand Rajasthan to TIFR Bombay, then to FermiLab in the US, CERN Geneva in the Europe, and then to IISER Pune. We did a deep dive on understanding what it takes to be an experimental physicist. We discussed about the role of conceptual understanding of various topics in physics and science, and how it actually can help in doing some cutting-edge experiments. She further revealed her understanding of doing mega science projects in large collaborative networks and how it has influenced her thinking. Also, there was an interesting discussion on the role of mathematics and statistical analysis in experimental physics and how we use it as a language to understand beautiful science. We discussed about mentoring of students and how learning is a two-way process in such an interaction. We also discussed why it is important to be aware of history of science and how it can make us better scientists. And finally, there is a small and nice segment in Hindi in which Seema explained about her research and motivation. The show notes, of course, contains all the references and links which were part of this particular discussion. I encourage you to have a look at it. Seema is a very valuable colleague of mine, and over the past decade or so, I have had numerous and enjoyable discussion with her on science, research, education, mentoring, and many more things. So, as I expected, this conversation too was thought-provoking and very enjoyable. And I am very sure by listening to this particular conversation with Seema Sharma, you will get an imaginative glimpse of experimental physics, which is truly a fascinating area of science. This is Pratidhwani. Listen as we humanize science. Welcome to Pratidhwani. Today I have with me Seema Sharma, who is a reputed physicist, an experimental physicist, and I'm delighted to have her on the podcast Pratidhwani, where we try to humanize science. Welcome, Seema.
Hello, Pawan. Hello, everyone.
So, Seema, you have been an experimental physicist, and your experience as a scientist is something which we would be very eager to know about. So, can you please tell us a little bit about your education and how you became a scientist?
Okay, so that's a long story, I would say.
Yeah, please.
So I don't know where you want me to start.
Maybe you can just get started with the school days. What really motivated you towards physics and science, for that matter?
I think I would say it was science in general, and perhaps came from I think it's a mixture of things. So basically, I grew up in a small town in Rajasthan.
Okay.
The place is called now Rajsamand. It's a small district. At that time, it was like sort of Kankroli, a small tehsil we used to call it.
Mm-hmm.
So the schooling part was very important because sometimes just the small things click. Okay, so for me it was more of in class, I don't remember, it was class 6 or 7, one of our school teachers showed us the onion peel under a microscope. And that big-like structure which was in the book, that was under the microscope. And that was the thing which sort of got me interested in. But there were more sort of observational and some collection, like for example making a herbarium file where we would collect variety of leaves and sort of flowers and all. So there was no physics per se, but it was more about like start observing the things and start connecting the things. And then at home, I think the parents were quite ambitious about us and they wanted us to study and focus on education. So even though I did not come from a very educational background, but that I think made a difference. So they were like, they wanted their daughters to go into science and their kids to go into science and go for it. Now, what was their motivation? I don't know.
Okay. Now, but generally, this was in Jaipur or?
No, this was in Rajsamand. I'm talking about when I was like really still school kid, like class 6, 7 kind of. Okay. So even those small exposure and experiments made a huge difference. So that's why I always say that, the right exposure at younger age is much important than all these hi-fi or really sort of art instruments we talk about in our research. So at the school level, doing the things is very, very important.
Absolutely. So how was your schooling? Like you really had kind of a education where the school was very well equipped, or how was it generally speaking?
So it was funny. So when I started with the school, it was a very small school. I think till I completed my class 12, it was still like a small up to class 8 school. So it was like up to class 5 that. And then class 6 to 10, it was in another school. And there, I think we were, so it was funny. So that school has both the state board and the CBSE. So I was into the CBSE, number of students were small. So we got like full attention of our teachers.
Okay.
In fact, some of the school teachers I'm still in touch with.
Wow, that's nice.
So, and there was one teacher and she has been like sort of one of her favorites, Mrs. Prerna Jain. And she would arrange even the books and all the reference books and for us from here and there. Because we did not have that access at that point.
Yes.
So that like the role of teachers in that time was extremely important for me.
Very nice.
They were the ones who would tell you, you can do it, just move out from here. So, and then class 11th and 12th, there was in a different school, that's called Lakshmipad Singhania School. And there I think the lab exposure was very good. So that's where I did my 11th and 12th. I do feel that the initial language, the initial education in your mother tongue is very, very important.
So
for me, the class 5 up to 5, it was all Hindi.
Very nice.
Class 6 to 10, I think my social studies was always in Hindi.
Okay.
Physics, like science and maths was in English, but then you can still catch up because there was no one at home to teach at that level. I never went for any tuitions. So sometimes that mixture, I think it helped me.
Yeah. And this aspect of learning in a mother tongue especially has very deep implications.
I think it has. That's my personal experience, but I think there is a huge pressure now of like, my kids should know this, my kids should know that.
But the issue always I find a little bit difficult is the vocabulary.
That I still don't have any better.
No.
I never appeared for GRE, so I never sort of mugged up those lists. But then I think communicating effectively is different than having like a large list of words in your vocabulary list.
Absolutely. No, I mean to say, for example, if you have a science taught in Hindi, then the vocabulary would also be different, right?
Yes.
Because that's something which probably is some attention is needed in that direction.
Yeah. So up to class 12, I was in Rajsamand only. And my first exposure outside was when I went to my university.
Okay. After 12th, you moved to...
I moved to Jaipur. So it was in Mahani's college.
Okay. That's a very reputed college, right?
That's a very reputed college. It was also like I got the admission into the physics, chemistry, maths. And then I sort of like... Can be frank here if it's fun or no, I don't know. I would say that other students, I would say don't be so biased. But I think I was like, no, I don't want to do chemistry.
Okay.
So then I think it was a bit late in the like whole procedure, but I think class 12 marks were good. So the HOD then allowed me to shift to the physics honors.
Okay.
So I had physics honors and maths.
Yeah. That's very interesting.
Yeah, that was again the less number of students. So we got a lot of one-to-one attention from our faculty.
But, as an experimental physicist, you cannot escape doing a bit of chemistry, right?
Why do you say so?
No, because I'm sure we'll come to that part of your research. Because, you're working at CERN and other places where there is a lot of instrumentation, there's a lot of material science also.
Not only that. So, this time when I went to CERN a week ago, one of my colleagues took me to one of their material science labs.
Nice.
And that time, first time, saw what the material science might mean, because you have no exposure of what it is.
Yeah.
So even there was some sort of epoxy, some sort of these small pieces, and I could see there are at least like 50 of them with different combinations, with different colors, different textures. So yes, you can't escape chemistry, but whether I directly use in my day-to-day research, I don't.
Yeah, that's right.
We need to know, in fact, it's more of the material science, but not of the chemistry, I would say.
Yeah.
Like how the particles interact with the detectors.
Yes.
That is a part of our...
Yeah, but if you go further deep down, it actually combines very deep physics and chemistry at that particular level. Okay. No, that's something very interesting. So tell us a little bit more about your college education. Like, how was it? And
yeah, so in college, so I started with the BSc in Maharanis College, and I continued there. It was an interesting experience because it was the first time that I was out of the home. And things did change a little bit. Ours was like this annual sort of system, so exams once a year. Now when I look back, I think it was useful because we had the whole year to think about what we are doing. So before the exams, the preparation was just for the exams because I have to maintain certain mark sheet level. But the whole year, the Maharanis library was excellent. Okay. It was very good. Mm-hmm. So that helped a lot. And then the labs were very good.
This is something which is very important. At an early age, if you're exposed to reasonably good quality laboratory,
yes,
that has some deep implication.
Yes, it has deep implications. Like even in school, I think I still remember dissecting these poor rats.
Oh, wow.
During the bio experiments, which I think people don't get to do now.
Wonderful.
So that had some impact.
Yes.
Yes. So Maharanis College also, I think the labs were compulsory, especially when we were doing the honors. Mm-hmm. And the teachers there made an effort that not only that we just do our experiments, but also be able to explain it to the rest of the class. Mm-hmm. So actually that's what I picked up from there, what I tried here also, and that works.
Yes. So I know that you also teach undergraduate courses, especially at the beginning of the undergraduate level, which is probably one of the most important foundation courses. And this aspect of live demonstration, I think, in my own opinion, also it's one of the most important and effective ways of teaching physics. And I'm glad that you're also using that.
Yeah, that is very important. And also the students be able to, my point is that, okay, fine, you do your one experiment thoroughly, explain it to class, write a report, then rest of the things you will do anyways properly. Yes. Because you develop that habit now, right? Like how to observe it properly and thoroughly.
Absolutely.
So I think that's effort we have to make.
Absolutely.
Now with the number of students always being large, but they will always be large. So we have to catch up with that.
Absolutely. So during this time, then you were kind of already deeply involved in doing experiments, or you had already decided that you're going to become a physicist?
No, nothing like that.
Okay.
So because in the college it was like limited time, like we have the lectures and then the labs almost every day. And the hostel was interesting because by 7 p.m. you have to be inside the hostel, so there was no chance of interacting with or discussing with all the people and all that. Mm-hmm. Other students or people who were what we used to call day scholars and things like that, right? So I think what I liked there was, I can't say that time that I was more inclined towards experiments or my lecture courses.
Nice.
I think focus was on both.
Focus was on both.
I think what I I know when I look back, I thank my teachers is essentially to give us thoroughly that, okay, fine, you have to do it yourself. Mm-hmm. Mm-hmm. So even solving those problems, be it like in the quantum mechanics, the double potential well, I think it still stays with me, although I don't think I'm going to solve it now.
Okay.
And I don't even know whether I'll be able to solve it now or not, but I think those are the things which really gets a part of your being you.
Absolutely. See, part of physics education generally has an important component of quantum mechanics. And given that you are a particle physicist, that is one of the most foundational kind of background you will have to have. I also had a background beginning of my MSc and also even, of course, in BSc, a lot of atomic molecular optical physics and kind of foundational quantum mechanics. And I've found that people who study quantum mechanics either can take a very deep root into theoretical physics or in certain cases something else.
Yeah, so that's an interesting point, right? So the point is that the quantum mechanics, the way we are introduced, is more like a formalism.
Yeah.
We just make one example of maybe the black body radiation and one of the photoelectric effect, and we say the quantum mechanics came up.
Yes.
We tend to forget there is a whole sort of at least 3 to 4 decades of work which went into getting those,
Absolutely,
at least establishing the facts,
Absolutely.
the experimental observations.
Absolutely.
Right. So for me, the quantum mechanics actually became more enjoyable after I did the courses on the molecular spectroscopy, atomic and molecular physics, and nuclear physics.
Nuclear physics. Absolutely. In fact, even...
Until then, I don't think anybody I don't think I had any feel for the quantum mechanics, what it can be about.
Very true. Very true.
So even seeing those, if you remember, our times we used to have those spectroscopy labs and we used to develop those films, right?
Yes.
And seeing the sodium doublets and coming out, I think that was it.
Absolutely.
So the quantum mechanics for me, solving those complicated problems, I don't think I can still solve complicated problems. I was never trained for that.
Okay.
But to be able to relate the things.
Absolutely.
That's what was more enjoyable.
Yeah. And it gives a kind of a very different and a deep insight into how a physical system works.
Yes.
Right? Because until then, most of your world is classical.
Yeah.
And suddenly, around BSc, you will get exposed to quantum mechanics and special theory of relativity. And these are, probably the most important changes in the mind.
So even the special theory of relativity, when we talk about it, I think the way we are introduced again in the college first year, second year was like either in the classical mechanics course or some electrodynamics course or something.
Yeah.
But I think that made more sense when you look at it all together, that you go for the advanced electrodynamics and start seeing these radiation effects, all the retarded potential and all that.
Yeah.
And really see the applications in the accelerators and all. And also in the particle physics.
Yes.
So I think some of these are very basic sort of concepts which has the wide applications.
Yeah.
Group theory is another example.
Absolutely.
I think unless we have that broad exposure, I think that's
sometimes.
I don't think I can say that, I would have enjoyed physics that much.
Absolutely. I have similar kind of thoughts here.
For example, maths for me was always as a tool. I never into one direction.
Yeah.
We had the papers one after the other and I would just enjoy it and finish and
absolutely.
Done with it. But the physics was more fun to be able to cross-connect.
Yeah.
So I think in fact I was talking to one of my students and I was like, look, to make you aware of the things is my responsibility. If you come unprepared for anything, then it's your problem.
Yeah. Absolutely. In fact,
so that exposure is important in my mind.
Absolutely.
And at whatever level, be it school level, be it college level, be it master's level, anything they say.
True.
That's what my personal experience has been.
Absolutely true. Absolutely. It's also, since you mentioned about the mathematics, people should probably be aware, especially some students and other people who may not be still kind of exposed to complete aspects of doing research, that experimental physics use a lot of mathematics. Just that they probably would not be using it in the framework, let's say, what a theoretical physics people use. Do you also kind of have that kind of mindset? Because in my own research, of course, I do use quite a bit of mathematics, but in a slightly different way. For example, Fourier transforms or some kind of analytical aspects and other things. Yeah.
This brings to my sort of master's level education, I would say.
Okay.
So I think the exposure to theoretical papers or subjects is much more to all of us.
Yes.
Right? So for me, the particle physics just did not come out as only because I was solving some QFT problems or something like that, right? I think the sort of what got me interested was essentially this nuclear physics lab, which was very good in Rajasthan University.
Yes.
Fantastic experiments. And we were given full time to sort of be on it. And also the side by side going on the lecture courses.
Nice.
Right, so that sort of helped me much more as compared to only having done theory or only having done experiments.
Yeah.
So I would say that at least the basic part of my field I would be able to sort of handle and explain to my students, okay, fine, what is going on.
Nice.
Okay, so that understanding is important. I might not be the person who would be interested in extending it beyond or come up with a fantastic theoretical new idea.
Absolutely.
But I think the theoretical part is important because that gives you sort of how to formalize the problem.
Yeah, true. In fact,
and how to formalize your observations to be able to sort of expect that what is next coming.
Absolutely. It gives you a very nice framework.
For me, it is a debating tool.
Yeah. No. In fact, for me also, mathematics is essentially a language.
Yeah.
It's a very effective and powerful language to do research.
Yeah. So I think I'm more into this sort of data analysis, but then it helps in the sense that, okay, fine, when I'm looking at my distributions, okay, fine, there is a physics clicking in that, what is happening.
Yes. And I also know that you use a lot of computational resources as part of your research. So during your education, you had some exposure to computational aspects.
It's mixed in the sense that, in the school itself, at some point we did some gates and logic gates and all that. That was fun. That was super fun. But during college, I think university, we had one course, which was the language used to be basic. There was one theory paper in BSc also, but not that much of exposure. In fact, I got my first email ID also in my end of my MSc first year.
Okay.
And that too because I was applying for a summer school somewhere.
Okay.
So the thing is that, fine. At that point, we had some, I would say, the book level knowledge. That helped to sort of build up the logic. And the fact that, the logic is more important when you want to go for the computational one or want to talk to computer. I think that stayed with me for a long time.
Absolutely. And that's where probably maths education also helps.
It helps a lot.
It helps a lot.
Because
logical way of thinking and deduction, etc.
So, for example, I think what we miss out right now with, even I have lost that habit now, that earlier, now it is like any syntax you have to look at, you will just go to the Google and just do it.
Yeah.
But I don't think even my PhD supervisor would like that. Because you have to understand what the philosophy of the language is.
Languages, yes.
What is sort of logic is. Then it's fine.
Which language do you generally use for your...
I think I'm more exposed to C++.
Okay.
But now people are moving to Python more.
Python,
I still have to catch up
that's
with it.
But
I know that internally it's C++. So.
Nice.
So it's a mixture of exposed to some parts of it, but not really hands-on into
it. That's an important thing. So now that you have laid the foundation during your BSc, mainly as an honors physics student, then you move to MSc in the same university?
Yes. So I think I applied for a couple of, but I couldn't appear for a few exams that time, which I applied for.
Okay.
I think... I am forgetting what was the reason. I think I got severe jaundice and I just could not. And then I just have to sort of found out one day that I have to go and appear for the Rajasthan University MSc exam.
Okay.
So that was an by entrance.
Yes.
And just got through that and I just joined the program.
Joined the program. It's very nice.
And I think it was a good decision.
Yeah, because I also know that Rajasthan University has a background in nuclear physics. There is quite a bit of work which has gone in the past.
I think the Rajasthan University, the way whole syllabus is, I think it's a very good exposure at the MSc level. Both BSc and MSc level.
Very interesting.
So I don't think at that time I did any kind of very advanced courses like what people do now. Even now, string theory in their MSc, but I never did those kind of things. But whatever we did was
very
thorough.
Very thorough. Yeah, I had similar experience. Yeah.
And the syllabus was very good. That's what I said, that fine. Until the MSc level, the exposure is extremely important. If you start narrowing down at that level itself, because you know it, right? The research now is not about like a single subject.
Absolutely.
Or a single topic. There's a lot of crosstalk which happens.
Absolutely.
And more than that, I think it helps you to build your own reasoning over the time.
Yeah.
So that's why I personally feel exposure is important.
No, I agree with you because even for that matter, if you're working at some topics which are at the interface of disciplines themselves, that is also an important thing.
And when I say exposure, I don't mean n number of topics.
Yes.
It's more about some subjects, but thoroughly done.
Yes. I agree with you. In fact, we see that also as as teachers and as researchers. That's an important thing. But these are all very important foundations, that would probably serve you all throughout your life as a researcher. And
so, for example, even when you talk about the computation and all that, right? Now we don't care for the memory or the time. The things are like sort of the computational resources have like grown up so fast and so is readily available. But even doing those numerical analysis courses and talking about what are the approximations in this rule, that rule, and what errors you are introducing, I think that was helpful.
Okay. That's good to know. That's very, very nice. So now that you're now finishing up your MSc, you're really now probably making a transition and thinking about going towards research. And that is a very important transition for any student, especially MSc to PhD transition is also not an easy transition. So how is this? How is it for you?
So if I tell you the honest answer.
Yes, please.
Even until I think the end of MSc, not end of MSc, I think first year, I had no clue about what the research is and where TIFR existed.
Wow. Okay.
Okay. So it just so happened that there was some ad about some summer program, not even a school. It was in IISc.
Okay.
So that was in 2001 summer. So I was selected for that thanks to some of my professors there.
In Rajasthan, in University of
Rajasthan,
Rajasthan.
yeah.
Okay.
So it was Professor Rashmi Raniwala and Professor Sudhir Raniwala. So I just contacted them. And I just went there, and that was my first exposure to what research can be.
Nice.
So there, that summer I worked with Professor Anant Narayanan at IISER CES. Yeah.
Very nice.
So it was more of a reading project. And
This is in CHEP, right?
Yes. No, it is called CHEP. Earlier it used to call CTS, the Center for Theoretical Studies.
Theoretical Studies, yes.
So there also you can see that I was still exposed to more theoretical part. But the thing is that he sort of encouraged us to read about the various symmetries and all that, but also about how to measure them.
Very good. Very nice.
Okay, so it was a reading project. The first time that I was handling the computer so much, not for the computing or something, just browsing through.
Okay.
So it was fun. So it was like 3 of us students from the different, and in fact, we have like in Resonance, we published 2 articles based on that series of 2 series. I'm sorry. So we actually, based on those experience in reading, we actually published 2 articles in Resonance.
Nice.
So there was a summarizing what we were reading.
What you're reading.
Yeah, so then I can say that Anant is my first co-author.
Nice. No, this is something which is very important. A lot of students do get research experience and exposure during a summer break, especially university students.
Yes.
Okay, even when I was studying, this was one of the crucial aspects of my education. And that really has a very deep implication and exposure.
Yeah.
And that is an important program to conclude.
Yeah, so at the end of Masters, so after this IISc thing, I just came back and I appeared for the JRF exam. I was actually selected for the BRC also, training school.
Training school, yes.
But the results were delayed, the semester was late and all that, so I could not join. And then I think I was selected in TIFR, then I did not bother about other things, so they would be fine, I will join. But I think at that point, my mindset was essentially I have to get into a job. That was like sort of... when I was writing my MSc exams, it was just like that I have to sort of go for a job, be it lectureship or school or whatever it is, because I had to be on my own at some point. But then I think one of the professors is essentially Sudhir Raniwala. He suggested me that, okay, why don't you go for research? You can do it.
Nice.
So I think, okay, fine, I can't really, and parents are not going to allow, and all kind of excuses, and he just sort of dismissed all of them.
Okay.
And then I had the option, like, I had the JRF, the position, I could have utilized that and stayed back in Rajasthan. Then it was the TIFR. So I think then just worked out that, okay, fine, I will just join TIFR and see.
Okay. And how did you get through TIFR? You know, one of the
exams.
Interview is kind of renowned to be tough. How was it?
To be honest, I don't have much memories of it.
Okay. So which means that it is all fine.
No, I think it was okay. I mean, I came out with a nice feeling. The questions which are asked, I think that interview was very good because, I mean, I don't remember all the questions and everything, but I remember the feeling I had that it was nice.
Nice. See, that's
I felt good.
You'll generally not remember good interviews.
Good interviews, right. So it was like sort of, they asked for a variety of covered quite a few sort of subjects and topics and all.
Nice.
But they made me feel comfortable. And they're okay, fine, we know you know it, just go ahead.
Wow. Very good. Yeah, that's a good thing. That's a very good thing to...
And the TIFR also, I think, by the time I joined TIFR, I think I was clear in my mind that I will go for particle physics. So that was my bias.
Yes.
Which I tell students not to be that biased, but then I was. But what I was not clear about is whether I want to go for theory or experiment.
Yes.
Basically, phenomenology, or I still had the insect of the pheno in my mind.
Okay.
But I think it's sort of the exposure there. What we had what we call the lab projects kind of thing, and that was very, very helpful.
In TIFR.
In TIFR.
Very nice.
That gives, for example, I think I worked in one of these non-linear optics lab also, then particle physics lab also.
Wonderful.
Did some lab view also that time.
Yes.
After that, I never touched it, but I did that.
You did that. That's an important exposure.
Some of those things, I think, there was a good exposure to have.
Okay. So tell us a little bit about your PhD research. What did you do? What did you learn? And what kind of questions you are interested in?
Yeah, so once we had our coursework done, actually, more interesting part here is that when I joined TIFR, I think most of my friends wanted to go for theoretical physics.
Yes,
and I think soon after that I was clear that I want to go for the experimental.
Yes.
So only a couple of us who were sure that who want to go for the experimental. Anything related to that. So I opted for the experimental particle physics. My PhD problem was more about, so I started with some sort of, So after we finished our coursework, we have to sort of opt for one department.
Okay.
Even there it was not, I think we have to choose supervisor directly. So we had enough exposure, like the initial semester we were doing coursework and all. I think one interesting thing was going to Ooty for a field trip.
Okay.
And there we did some experiments and so on and all. It was fun. So
Nice.
about this grapes experiment and all that. Since I was already interested in particle physics, I think I had two options when I went to TIFR, either to join the Bell experiment, which was ongoing, which is an E plus E minus collision factor. And the other was like the LHC, which was coming up.
Wow. So just for our listeners, can you please expand those terms because that is important. Yeah.
So in the Bell, they are colliding the beams of the electrons and positrons.
Nice.
So you have nice clean, and that was the program already going on.
Okay.
But in the LHC, which is a proton-proton collisions, it was still to come. So when I started my sort of projects, so I joined TIFR in 2002.
2002. Okay.
So at that time, I was like, okay, fine, we will have LHC starting by 2005. It got delayed further anyway.
Okay.
So after my coursework and all, I contacted the department chair. It was Professor Somnath Ganguly. And I was like, okay, fine, you can talk to whoever you want to sort of join and all. I was already doing projects in that department.
Okay.
So then I talked to Professor Shananda Banerjee and he says, okay, the CMS is coming up and it will be an interesting experience. And I was like, okay, fine, let's go for it.
Wonderful.
So I don't think I had that much of exposure what I'm doing, but I just agreed, okay, fine, let's go for it.
See, a lot of times this is something very important because, even at the cusp of starting a PhD, you will be probably going with not complete information of what you're going to do. That's, something very exciting. A very similar experience for me too. Yeah.
So it was interesting. My first project there was the TIFR, the group was building up the scintillator detector, part of what we call the outer hadron calorimeter.
Okay.
The TIFR group was responsible for it. So I got to do my first project on that with one of the professors there.
Okay.
And I think I really learned like what the data analysis is, how they do it. It was basically related to source which passes through the whole long scintillator tile. And you sort of calibrate it, like how do you make the uniform signal output. And the second project was more on the analysis kind of thing, but it was like partly Pheno kind of, I would say. But not Pheno in the sense developing anything new, but it's still no data. It was essentially PP collision and trying to look for some supersymmetric particles in that, which was essentially based on the simulation. My third project was actually with Professor Shananda Banerjee, and it was more on the detector physics. So when I say detector physics, it's not I'm talking about the instrumentation, but trying to understand how the particles are behaving in a detector.
Okay.
And that was, I think, my first exposure to calorimeters, and I think that's where I got hooked to it.
Okay. And that time, you would have already finished your coursework?
Yes.
And you had some background in high energy physics?
Yes. So background in high energy physics started from my MSc only, because particle physics was my special paper. So introduction to the nuclear physics, the quantum field theory, and the particle physics, and the sort of ingredients which go in building up the standard model, that was all from the MSc. But here I also again redid the QFT and particle physics courses.
Wonderful.
At the TIFR grad school also.
Wonderful.
Okay, so then I think I decided for like, fine, let me try for the CMS and the data will come. But so my project then became, over the time, it comes out like we were actually testing the hadron calorimeters with the real particle beams. So it is not the PP collision, because LHC was like, we are not having PP collisions, it was not there. But we get the single particle beams from what we call the SPS accelerator. And those we hit on the thin targets. Okay. And then all variety of particles can sort of be produced. And we can sort of like have a beamline and make them really steer towards the detector and study what detector is telling us. So it's really the performance of the detector establishing for the first time.
Okay, very nice.
So I participated in 2004 test beam, and then it was in 2006 test beam.
That was at CERN? Or
that was at CERN.
Wow, okay.
So I was there for the data taking and all. But then the data analysis and all, I think what I learned from there, it stays with me.
Stays with you. So tell us a little bit about your first trip to CERN. How was it? That would have been very exciting, right?
Yeah, so Shunanda was there, my PhD supervisor. So in that sense, I had a somebody there.
Somebody there to guide
But
you.
then I went in something I think it was in February or something like that. And it was quite cold.
Cold, okay.
It was first experience.
Okay.
But then, it was nice because I could. So they used to have a lot of academic lectures and all, training programs and all. So I used to attend those lectures. And lab exposure was... No, I think I started getting lab exposure. Not in the first trip though. I visited some labs with my supervisor.
Mm-hmm.
But in the following trips, it was more. When we were doing some of the testing at the actual site of the CMS detector.
Wow. Okay.
But that time it was more of the this computational based.
Mm-hmm.
But the exposure I got from there in the CERN library is still my favorite spot.
Okay. Yeah.
So that was fun. But that was the time I really get to work with my PhD supervisor really very closely one-to-one.
Nice. Very nice.
And also learn his dedication to his work.
Yeah.
Beyond this world.
That is something which all of us have actually heard about Banerjee. And do you want to tell a little bit about your experience working with him? How was it? He's a very well-known experimentalist, and
Yes.
the kind of training you got from him.
So for him there are no shortcuts to get any results. He would like to really thoroughly check everything step by step, and that's something commendable. But I think what I appreciate most is that he let me think my way.
Important. That is an important thing. Yeah.
So I was free to argue with him.
Yes.
So that was something which sort of, I
has also stayed with you.
It stayed with me.
Stayed with you, and
Moreover, also it was really I want to do it my way and I have these results. Okay, fine, let's talk about it.
Mm-hmm.
But he was not a talkative person or anything like that. So he was very quiet always.
Nice.
But,
I've heard him also in a colloquium at IISER Pune.
Yeah.
Fantastic, so illuminating, very interesting stuff.
So he is, I think, I would say that sort of part of my work style, actually I learned a lot from him.
Mm-hmm.
That you have to be thorough, there is no choice.
Okay.
When you are taking the data, I think one of the things is that essentially in any experimental field, if you talk about whether it's your or it's mine, you are losing money, right, if you are not doing it properly.
Absolutely. You're right.
Right?
There's
So
an infrastructure. Going back.
There is no going back.
Absolutely.
So that responsibility we have to take.
Yes.
So that building up your... whatever the outcome is, or whatever your experimental strategy is, or whatever looking at your results is, I think that's something which is sort of I learned from him.
Yeah, very crucial aspect,
Very
right?
crucial
That's a very important thing.
Yeah, and he just did not fine, let it go there. Okay, fine. Somebody's thinking that way or that way. You go your way. No problems with that.
Wonderful.
So I didn't feel any time the pressure of that why it is not done today. I think I used to be habitual of taking tension myself.
Right. Yeah, but that is kind of common to all researchers, so to speak.
Yes.
In that sense, there are a lot of people who are really dedicated to their work. They generally take.
And other thing is his commitment to his work. I think I still have to learn from him.
Yeah. That is something which is always commendable.
His dedication.
Yeah.
That's sort of beyond this world, I would say.
Yeah. So now you have, then at that point you are now going to CERN periodically, I assume, as part of your work? Or
Not really. So during PhD time, I didn't go to CERN that often. It was only, I think it was twice for the test beam experiments.
Yes.
And once for this project, which before I started the actual PhD problem. But the final year of my PhD was spent at FermiLab actually.
FermiLab,
my
yes.
PhD supervisor moved there.
Yes.
And then that was a different exposure altogether.
Yeah, tell us about that. In fact, that is also extremely reputed experimental laboratory.
Yeah, so I think the hadron calorimeter part which I was working on and the hadron calorimetry itself, I think we had many experts there.
Nice.
Okay, so that was a different level of exposure altogether. And really sort of different mindsets coming together to be able to deliver something. That's something which I learned very, very closely.
Nice.
And then there were other experiments, neutrinos and all that. The Tevatron was already closing.
Mm-hmm.
So there was some activity going on. But that 1 year, I think it was very productive.
Mm-hmm.
And I could really talk to the experts in the hadron calorimeters.
And tell us a little bit about just basic aspect of calorimetry. What do you mean? Because calorimetry generally in normal laboratories is very different.
Yeah, I should have said it before.
Yeah.
So calorimetry in general, we talk about this temperature change and measuring it, right? Whenever something happens.
Yes.
So in case of when the particles are passing through the detectors, right? We are talking about few GeV to few hundred GeV particles kind of, and these particles can be electron, positron, photons, or the hadrons like charged pions, the protons, the neutrons, right? They pass through detector. We want them to deposit whole of their energy in the detector.
Nice.
Okay,
Nice.
because when you are doing, for example, the other aspect of the detector is the tracking.
Yes.
Where you trace the particle and magnetic field from the radius of curvature, the bending, you can find out its momentum. There you don't want the particle to be disturbed because then the trajectory gets affected and your momentum measurement.
Yes. Yes.
But that has the limitation that you need huge magnetic volume there. So for very high energy these particles, we have the calorimeters, and the idea is to make these particles deposit their energy completely in these calorimeters.
Nice.
Now the temperature increase there is sort of cannot be measured.
Okay.
So the way we measure is that either it can be, for example, a scintillator detector, so you get light output, or it can be, for example, a silicon detector where you can get the current. They basically charge pulse.
Nice.
So you can collect the charge and how much electron hole pairs were generated.
Wonderful.
Okay. So these are the sort of signatures we get when the particle passes through, and from these signatures you want to go back and see what was the energy of the original particle which came in.
Wonderful.
Okay.
Wonderful.
Now the electron positrons, when you talk about, they just sort of as soon as they hit the material or just interact with the material in the presence of external field, if the energy is enough, the photons can pair produce E plus E minus, and the electrons, when they come across the external field, they get accelerated and they're still photons. So then there is a huge sort of the shower of the cascade of these electron positron photons in electromagnetic shower.
Yes.
But it's all the electromagnetic part of it. Okay, so these detectors you can think of they will be linear, less issues.
Okay.
On and sort of broadly speaking. Right? There may be details which will come to you leave it for us.
Yeah.
That part. But for the hadron calorimeters it's quite tricky. Because when you have these particles which are passing through the detector, they sort of have also the nuclear interactions, and then again the shower develops, which is again the particles which can be other hadrons.
Nice.
But it can, if it's, for example, you produce a pi zero immediately decays to 2 photons. And then you have the electromagnetic shower component. So the hadron calorimeters has these two components, and event by event fluctuations is huge. So the resolution is worse. Okay. So to understand this one and then be able to sort of put it properly in the simulation, that we understand the simulation also, because simulation is important for HEP experiments.
Yes.
Okay. So that is where these calorimeter detectors come in picture, and that's where the challenges come in picture.
Interesting. Very interesting.
So the hadron calorimeter part is something which I have been interested in all through. And in fact, one of my previous students, he graduated with his thesis on
this
upcoming calorimeter technologies.
Yes. Very fascinating.
That is for the high luminosity LHC.
Nice. So now you finished your 1-year stint at the FermiLab as part of your PhD. And then what was your further move?
Yeah, so then I think I was, as usual, with the grad students, getting stressed out what to do next. But then I just got lucky that at that time I could get one slot I applied for the FermiLab postdoc position, and it worked out before I left.
Wonderful.
I came back to India for submitting my thesis, and sort of I was selected. So after I submitted my thesis, I went back to FermiLab as a postdoc.
Wonderful. So you're then going back where you left it, and then you joined the team again.
So again, it was like LHC should start, but it started, but again met with an accident immediately. There was some issue with the one of the magnets benched, and there was an accident. So it took almost 1 year to repair it.
Nice.
And then it started again.
And
back so I joined in end of 2008, around October 2008, when the accident happened in September 2008. And then it started again in 2009 when we had our first data. So in that sense, I can say that I think I was one of those who were looking into the first collision sets which came out, event by event. So that was the excitement, which was different level.
Absolutely. And this is all in FermiLab. It's still.
I was at FermiLab.
And then.
So then I started traveling to CERN very often.
Yes.
For all the sort of collaboration meetings or for the data taking time, and I was part of some prompt feedback group and things like that.
Yes.
But FermiLab had all the resources, right? It was what we call in our the computing storage and computing infrastructure in CMS, we call it tier 1. And that time I think I had an access to each and every event right there.
Very nice. Very nice.
So the FermiLab resources were like the key in the beginning.
Yeah, that's probably at the forefront of a lot of experiments being done.
But then I think the importance of my PhD work I did not realize until late. Because the kind of work we did, we also used the same data to tune the Gian4 simulation for the CMS.
Nice.
And when the first data came out, that handful of events, and the performance we saw in data and simulation, I think that was fantastic.
That was always fascinating, and you really get very motivated about it. So in this context, you would have already kind of now got a very broad understanding or at least exposure to high energy physics, right? And that understanding generally takes a lot of time, right? It doesn't happen very quickly. So during this time, were you also reading widely apart from the problems what you're working on? Yes. Or how was your...
Yes, so even during PhD, I think I always say like the TIFR, we got very good exposure.
Okay.
Right, the number of talks I heard there or number of random papers I went through, even the original papers where somebody were talking about like find what jet fragmentation is about.
Okay.
I think that was quite useful. Because if you see really like unless the LHC started, I did not have any experience on the physics analysis for any new physics search or the standard model measurement. Right?
Yes.
So I think that reading was more of the like the physics part of it, that okay, read this, read that, talk to your fellow colleagues. That exposure was very good. But also I think I was just like, I used to like reading anyway, so I used to keep random stuff.
Random things. That's so crucial, right? Because even during the PhD time...
Yeah, so I would read a lot of non-physics also.
Non-physics
Some
also.
novels or something.
Oh, wonderful. We'll come to that. We'll come to that aspect later.
Yeah, so I think so what was missing in my experience until now, in the like first year of my postdoc gets over, but there I was already deep into the like getting the... See, you have to understand, that's such a big system. It's really an engineering marvel.
Absolutely.
The CMS experiment. But having it all together and you are looking at the data for the first time, you don't know what happened initially, right? You don't have what went in. Only thing you have the output from your detector and you want to figure out what happened in that collision.
Yes.
So all these challenges of the calibrations and detector is working well and all, I think I could contribute to that, and that was quite enriching experience.
Absolutely.
Because you become responsible for the whole thing at some point. And the good thing is that okay, there is a full structure, right? Other people are also reviewing and all that. So that fear of being questioned, that was always gone.
Wonderful.
I was like, I just want somebody to look at my stuff.
Yeah. So
that was very nice.
That's a crucial element when you're...
So I think getting some of those first distributions of the, like what you were seeing the data, that was fun. But actually I started building up more on the physics program only after that.
See, one of the elements of doing experiments, and this is also true when we do experiments in the laboratory, small laboratories, is the importance of statistical analysis. That is something also of paramount importance in your work. So how much is the kind of training a student gets in such kind of analysis most of the time? Is it on the go, or you do have some kind of a training for students?
So are you talking about my part or now?
Yeah, no, generally speaking, in high energy physics.
Yeah, so we do have some exposure to the formal statistical courses. But statistics is one subject which you can never learn just by reading.
Absolutely.
You have to apply it.
Apply it. I agree.
Okay.
I agree.
So even there also, like the things have become advanced and easily the packages are available. That's something again I learned from my PhD supervisor. He will make me do it on your own first and then worry about the packages.
Nice.
He would say, okay, why can't you write your minimizer? I was right. I mean, why can't I write it?
Okay. Nice.
So
that's a crucial element. In fact, that's something which is very important, and increasingly, with all the new computational progress which has been happening.
Actually, unless we do it, we don't even know where we are splitting the hair, or where we are making the approximation correct or not.
Yes. Yeah.
Because you have to find a balance somewhere, right?
Absolutely. This is something which is very, very important. Very important. So, in that sense, you would have also interacted with a lot of people across the world. First of all, in FermiLab, where you are already working during your postdoc, and you're also traveling to CERN. How was your kind of experience in, it's essentially totally an international effort in these laboratories. How was your experience working with the teams which are so large? Generally, the experiments, what we do in terms of small laboratory experiments, in my own case, of course, when one goes abroad, meets people, goes to conference, you do interact. But in your case, in such a large laboratory, your day-to-day functioning would be with a very large group. How has been your experience in that sense?
So there are two aspects of it, right? Depending upon, so as a junior member of the collaboration, when I was as a PhD student or as a postdoc, I think we were still working in smaller groups.
Okay.
Right? So the actual project which I am responsible for, like delivering for the collaboration on behalf of the collaboration, we still have the smaller group. Although the analysis which I worked on were still like sort of a bigger group, which would be like 20-25 people, but it's still limited, and we had our tasks defined. But only doing my piece doesn't work, because we have to have all the pieces to come together to call it a final result.
I agree.
Right? So I think that was a very sort of useful experience.
Okay.
In the sense that, okay, fine, working together, whatever your personalities are, whatever your cultural part is, when it comes to the science part of it, you are just thinking together.
Absolutely.
And moving ahead together. I think that was the most sort of enriching experience for me.
Very nice. That's actually a very crucial aspect. Because
that is correct, whether you do this small group like your kind of experiments which can be more tabletop, or whether it's a wider community. But later on, I think when I interacted more in terms of like my roles as the convener, group conveners and all that, there we were interacting with much broader group. But there again it becomes, okay, fine, at the end you are working together to get the results put together and out.
Yes.
Right?
You're right.
So that is sort of a very sort of, I like this aspect of this my particular field, research field which I'm working in.
High energy physics, especially experimental high energy physics, is also known for our papers which have many authors.
Yes.
Okay. Do you want to tell a little bit about, because this is something which even within physics community people don't have complete appreciation. Do you want to tell us a little bit about how generally a paper is written in such fields?
So again, I said, right, for example, I have worked with papers where there will be like 25 authors in like key people who like meeting almost every week kind of, 20 to 25 kind of. I would say 20 more likely. But I then have done also the papers which are only my students.
I've seen that, yes.
Right, so there's very limited, like maybe one postdoc involved or one colleague involved and my student in here, right? So in both the cases, I think it depends on the like how fast or slow and what the collaboration requirements are. It all like sort of timing or everything matters. So, but once we do the analysis, we have to present in our what we call the meetings. So, one is the working group meeting, which is my day-to-day interaction or weekly meetings, and some colleagues all across the globe. And with my students, I am dealing with them every day. I try to meet them almost every day. But beyond that point, we have to present in the physics group meetings. Okay, so there are like, for example, the groups focusing on the stand model measurements. There are something focusing on like new physics searches. There can be something on the more like the top physics. There can be more like the Higgs Boson, like the related studies. So these groups, each of them is sort of further subdivided into subgroups. Depending upon that can be the what kind of properties you are measuring, or it can be what kind of tools you are using.
Wonderful.
So it depends. So in these subgroup meetings is where we have to present regularly with updates.
Very nice.
Okay, so that gets reviewed by everyone, and the reason for that is that you don't want to have contradictory statements or information going out of CMS, which is using the same data and same detector.
Exactly. You want some kind of
coherence. Right? So that's why it is important. And other point is, it's so sort of advanced stuff, and that there is always something you can miss out. So it's good to have that. Okay, fine, things are consistent. For example, if you have to apply for the systematic uncertainty or some correction to your distribution, it has to be consistent.
Nice.
Otherwise, discovering new physics every next day.
That will happen.
That will happen, because if it's a detector problem, I will get a dark matter signature in terms of the missing transverse momentum.
Okay.
It's very easy, right? So that's why these meetings are important.
Nice.
And after that, it's an approval process that once the result has been put together, then we need to get an approval by this group, the physics group itself. For that, even we have to like prepare our documentation and everything, be available to the conveners and the reviewers. Basically, whole collaboration, because it's all via the database, which is accessible to all members of the CMS.
Wonderful.
Yes, and then the analysis. Once you say that the expert group has really done it, you want an independent review, and for that we have the analysis review committees. Those are usually like 3 to 4 members, and they thoroughly review it. Once they agree, ask for cross checks. If there is some problem, sometimes we find out problems working with them, because they are independent people. Independent, but experts in different fields and experienced people.
Wonderful.
So once that is done, we have to ask for approval from the collaboration. So this is what we call the approval presentation.
Wonderful.
Okay, so even there also at least a week before we have to make all the paper version and the some draft and the documentation available. Once that is done, the paper draft which is approved goes for the whole collaboration, what we call collaboration wide review.
Wow.
To make sure that at least somebody reads it. There are some 6-7 institutes they are assigned for the particular reading. So many times we do it for others also. Yes. And then it goes for the final reading where you make that everything is sorted and then it only gets published.
That's a really thorough.
Is very long
and also very thorough, right?
I think and it's good for the students, especially when they are taking a lead on it. They get variety of exposure, not only the presentation and everything, how to convey themselves, but also to be able to defend what they're doing.
Absolutely. That's such a crucial aspect.
The final paper which will go out will have all the CMS authors, because you see how many people have already paid attention to it. But not only that, the detector is built by others. We are using calibration factors or my corrections coming from the other people, the people who are dealing with the detectors, making it operate, making sure that everything is working fine, making sure that we are not collecting nonsense. So all these things are important. So as a policy of the collaboration, everyone
would be.
Yes. Yeah. But internally, we know it that who is taking the lead on it and who are the people involved. So we have mechanisms.
Very nice.
How to sort of say that who has worked on it.
That coordination is very important. Very
so outsiders, they cannot know. Sometimes within collaboration also we don't know what is going on. But in analysis notes, usually it is limited.
You will be aware.
But sometimes we have it many times that fine, they write this particular group. So then it becomes difficult to find out who is the person. So there are drawbacks and there are benefits.
Wonderful. So now you are finishing up your postdoc in FermiLab, and you were there for how long?
So FermiLab, I was there for more than 5 years.
Wow, okay, very nice.
And slightly more than 5 years before I joined IISER Pune. But
yes.
There, so once the data started coming in and we developed the full program for the hadronic searches.
Yes.
So basically no leptons in our final states. So I started a couple of programs. Mostly related to the supersymmetry searches. But then just moved on and I joined IISER.
Yeah. So now you're making a transition from a postdoc to a faculty.
Yeah.
How was that? How was your experience?
It was interesting in the sense that, fine. I think I was clear always that I have to get back to India. There was no doubt there. There came a phase where it was not clear what I want to do, in the sense that everybody was moving, many of my friends moved to industry. And then finding a job in academia is not easy. This one worked out for me, luckily. And I joined here, and I think within a month I was at home.
Okay. Yeah.
And then I think I started teaching and dealing with the students, and got lucky with my first set of students. They were all excellent.
I still very vividly remember your talk at the department.
My job talk.
It was one of the best I've heard, in fact, to be very frank.
Really?
Yeah.
In fact, that feels good.
Yeah. No, I still remember, because there was a guest house which was kind of converted into a lecture room hall. Yeah. And I very well remember that particular talk. That was a very interesting stuff. Yeah. So you also kind of moved into IISER Pune and also took leadership role in your experiments, especially in this international effort. Would you want to tell us a little bit more about that?
Yeah, so when I joined here, so as I said, there are different physics groups and different detector groups, and so somebody has to coordinate it.
Yes.
Because ultimately things have to succeed, and you know it, right? Even in our lab, where we have hardly 5-6 members, if you don't follow it up, then
it's gone.
1 week you don't follow, and we know that we don't know each other.
Absolutely.
Right? So I think it becomes very sort of important that things are coordinated properly. So I think when I joined here, I was responsible for one of the subgroups of the SUSI, this search group. Supersymmetry search group. But after that, I got the opportunity to lead the CMS JET-MET group. So the JETs and MET are essentially discovery tools at LHC. So JETs are essentially experimental signatures of the quarks and gluons. And MET, or the missing transverse momentum, that's a signature for something which went out to the detector without depositing any signature.
Okay.
So it could be neutrinos in standard model, or it can be some dark matter candidate or something which is not interacting. So we call many times broadly group as the weakly interacting massive particles, which can be the thing. And so that group is very it was a very interesting and I would say one of my most enriching experiences. In running experiment. If anything goes wrong in any piece of the detector, it shows up in these two.
Okay.
So I think every time, and that time also the time when 16 and so I was from 2016 to 2018. And that time I think the CMS also upgraded a few subdetectors and all.
Yeah.
So there were a lot of problems we were coming across. So it was challenging.
It was challenging.
It was
right?
challenging.
Yeah, because I knew that you were quite busy then because you had to also
And also it was
coordinate
my first such experience.
Okay.
I think now you ask me to do it again, probably I would be more casual about it.
Yeah.
I would still be sincere but not taking that much of stress.
yeah.
Because the experience matters.
Yeah. No,
So there I think talking to the different people that I was also dealing with the detector physics groups as well as we have to take, so detector physics groups where we take inputs from and physics groups where we have to, they are our users.
Users, okay.
Right?
Nice.
So these objects. So that was, I think, made me appreciate the people who are working there and making the whole thing successful.
Wonderful.
I think my appreciation for them actually came out there.
Came out. Very, very nice. Very
Until
nice.
then, we don't realize how these
the-
big collaborations work and how these big projects work.
Absolutely.
You need to have a core group who is like really 110% time for that period.
That period of time.
Otherwise, none of these big mega science projects or anything cannot work.
It cannot work without a very...
And it's not that every single person has to be there all the time. At that point, you have taken the responsibility, you have to be on it.
Yeah, absolutely.
So my appreciation for the people who are actually in the operations and the commissioning and everything, I think
It shot up quite a bit.
it's short.
No, because even with a small group, even people who take initiatives and do take some specific kind of viewpoints and
and also I think we have to sort of start appreciating or acknowledging the different groups, people sitting in the different corners of the world have their different strengths and different weaknesses.
Absolutely.
Okay, so we have to sort of bring out that what best we can get from them.
Absolutely right.
So it cannot be just like sort of a managerial that fine, do this one by n and done. It doesn't work that.
It doesn't work that. Absolutely.
And once I finished my JetMed convenership, I was given an opportunity to lead the supersymmetry group, which is again the physics group and mostly searches. I think that was again challenging in the sense that we were finishing our Run 2 program. That was the end of 2018. And we had a lot of data, which was the first time that we had such a big data set. And try to put it all together and get the results out, physics papers out.
Nice.
So I think that was fun.
Yeah. And also challenging, right?
It was also challenging, but then we have I think in both this thing, I would say that, I was very lucky to have very good set of people who were leading the various subgroups.
Nice.
Right? So that team was really strong in both the cases. In both these, tenures, terms.
Wonderful. So tell us a little bit more about what is your current research interest, what have you been working on, and what is your group also looking at?
Yeah, so after I joined here, we were it was the first time we were getting the data or the PP collisions at the 13 TeV, which is the highest energy, and now we are running at 13.6. So I wanted to continue with the new physics searches. So that's what I did with my students, like looking for the supersymmetry and the hadronic physics, which is more challenging. But also because it's more connected with the detector, with the problems happening, and also you have to, some of the searches are really understanding your detector properly.
Nice. Yeah, that's a crucial element.
That was a crucial element. So I enjoy those things even today. But then we sort of diversified into some of the adding one photon in the final state. That was, I think, first time we did it. In fact, when the referee reports came with my first student who graduated for the paper, when the referee reports came, it was it's for the first time done in the CMS and Atlas. And that felt good.
That felt very good. Right?
That felt very good. Yeah, so that way, I think we sort of expanded a bit, and still it was in new physics searches. But then we started talking about for the detector upgrade, the CMS detector upgrade for the high luminosity LHC run.
Nice.
So that is supposed to start at the end of this decade. But then it will be really as I said, high luminosity. So in last 10 years, whatever data we have collected, we will be collecting 10 times more data in those 10 years.
Wow, okay. It's kind
really
of
the intensity increasing. That means you have a lot of radiation. And especially forward detectors, they will be highly exposed to the radiation. So we have to replace the current detectors with the radiation hard detectors.
Nice.
So the technology completely changes.
Changes it, okay.
And calorimetry has been my interest, and this is an opportunity which came up that India is contributing to it, the India CMS group. So we have a silicon-based detector.
Okay.
So we have the layers of the silicon sensors, and then there is some sort of an absorber. Either it is the lead or for the stainless steel. And then behind that is again the scintillator detectors. That's a small scintillators with this very small pieces of like few centimeter by few centimeter, and they have the silicon photovoltaic press really mounted on them.
On top of that, it's wonderful.
So it's like sort of a piece which is beautiful.
Okay.
So then my student, he participated in the test wing in 2018, and he got interested in this thing, and it's one of the things which
was continued.
So I think it was Shubham was the student, and he already graduated this one. I think his work was quite appreciated in the CMS. He actually got the CMS Ethical Award.
I know
CMS Achievement Award.
Achievement Award also, yes.
So it's the CMS Award, not the Achievement Award, but I will probably correct this. Yeah, so Shubham also got the CMS Award for this particular contribution to the Ethical test beams and the pion analysis. So I think what we decided that now we had an access to the real data. Because we have again shooting the single particles in the detector. But now this detector is very highly granular, which we don't have that kind of strength in the current detector. So that allows us to really sort of take the snapshot of what is happening event by event in each shower.
Nice.
Okay? So then my Nexus student, she picked up, and since we have the handle over the data, we could really try this advanced machine learning algorithms. So we are actually using the graphical neural networks and trying to see that where we can improve. And the resolution can be improved by factor of 2, and that's something fantastic.
Wonderful.
So we are just sort of wrapping up that project and writing paper for that.
Nice.
So I think that project is very, very interesting and challenging. Technically, it's going to be challenging.
Yeah, because you'll have to implement
millions of independent channels without. So, but even I think that project will be more interesting as we start moving towards actually deploying the detector, is because calibration and all we have to pay attention in detail. So some of my master students have been working on those, and I learned a lot from them.
So what is the big picture, what you're trying to understand for let's say general audience, if they want to understand what is the big picture in this?
Big picture is that we want to understand, my usual statement in any my outreach talk has been that we want to understand what are the fundamental constants of the universe and how they interact with each other, so that we see the world around or the universe around the way it is right now.
Yes. Okay. Yes.
So the idea is that there are different ways of doing it. We know the established physics part, and we can formulate it in the sort of understanding so far in the standard model. So standard model is a theoretical model based on the quantum field theory, but it has inputs from almost a century of the experiments.
Yeah.
Right? So one is that to try to understand it better and better. Because whatever we have measured, it always comes with the uncertainty. For example, the Higgs sector or the top quark sector, we can still have a lot of margin there to reduce the uncertainties and try to say if there is major telling us something. Or go for the direct new physics searches. Okay, so generally what we're talking about, we know that the standard model is not complete. It doesn't explain many things like the dark matter, or it can be some calculations which are related to the Higgs boson mass. So we know something more is going on, right? So I can directly search for that. So there are various theoretical extensions of the standard model, but then they can predict new particles, right? So we can go towards that one, or it can be a two coming together, that you do the precision measurement and try to see if we can really constant the new physics scenarios.
Nice.
So the overall picture right now for me is essentially going after the what is going on beyond the standard model. But I might be slightly want to change my tools a little bit and want to go for more for the precision measurements.
Measurements and other things.
And the detector part continues, because that's not only my interest, it is needed for the students. Just doing only the high level data analysis in my mind is not sufficient, because they need to get feel for what they are doing. And secondly, we need to build up the people who can really understand the detector and build the detectors.
Absolutely.
Because to collect the data, we need the detectors.
Absolutely.
So I think that's sort of a mixed two-prong approach which I have, so that the students get the full exposure.
Full exposure for that.
So I'm not too much into instrumentation, but I do like to do some things hands-on for the interest of the students and training the students and understanding the system myself.
Yourself. So in this context, what is the current scenario in India? For example, if somebody wants to really do such experiments, large-scale kind of multinational experiments, is there some specific effort within India which is kind of targeted towards, or is there something which within Indian experimental situation there is a progress which has been made?
So one thing is very clear that we cannot have multiple LHCs.
Yeah, of course,
Right.
you're right.
But I think we do need to have something in-house such program. It's extremely important because we have decades of experience in the cosmic ray and then lab and then the LHC and Tevatron, Bell, quite a few.
Yes.
But there are other also experiments which are like more of the high ion one, like the RIC or STAR or ALICE now. So what is important, like the INO was in this direction, right? That you want to have some in-house one effort here.
Yeah, it's INO is Indian Neutrino Observatory.
Yeah. So I think that should be pursued. Unfortunately, it went into the different kind of problems, and I'm not sure actually what is the status
of that.
Proceeding further is.
Yeah.
But I think
Professor Nabha is really
Professor Nabha who was sort of heavily involved in the initial phase, and now Govinda Majumdar at TIFR, he was
nice.
I think he has been involved in it. But they have been trying a lot that I am aware of, and such experiments I think we need to encourage.
And
also I think, like, for example, there can be sort of like this kind of the neutron experiments are dark matter experiments. I think these things should be encouraged
a little bit more. There's quite a bit of interest for very large scale experiments. Even the LIGO has come up very
LIGO is coming up
here, and recently also there's a lot of Indigo is the one which is
so I think we have participated a lot. We need to really sort of now jump with our experience and do something. But there is a problem in the sense that we don't have any dedicated research facility in India. So for example, I think DAISY part, for example, which might be common interest to us. Like DAISY is a particle physics laboratory.
Can you expand the term? If you, I can always dig it up and
I think it's more of a it's a sort of the like CERN or FermiLab or something like these kind of facilities. DAISY is also one of them, but we can talk about CERN for example. Let's not get into DAISY part. Right?
Okay.
So CERN is still a mega
project,
like global thing.
Yes.
Right. But as a country, for example, we don't have any sort of research facility which can be really have variety of high tech or the state of facilities under one roof.
One roof, yes.
Right?
Yes.
And it's not about the facilities, it's about the expertise which is needed. Right? Because the energy kind of experiments, or in fact, for that matter, any condensed matter experiments or the optics experiments these days, they really go for the precision instruments.
Absolutely. You're absolutely right. Without that, it is not possible.
Without that, it's not possible to easily do it.
Sure.
Right? Yeah. So, and in HEP kind of like the variety of expertise have to come together.
True.
Right?
True.
Be it material science, be it electronics, be it building the detectors, be it radiation physics, be it particle physics. A lot of things have to come together.
Yes.
So, that's something which we lack. I think our common sort of example might be KEK. You went to KEK recently or no?
No.
So then I might be confused. Yeah. What I'm saying is that one such facility where you have, like, for example, the TIFR might have an access to, for example, Peloton, their facility and all. But what about the other university groups? How much access they have to the advanced facility?
Yes.
Okay. And it's not about like buying expensive equipment and keep it in my like sort of lab.
Yes.
It's about the expertise which sort of build around
that particular facility.
So for us, it is not like, for example, the data acquisition. We have to scale it up. Like in LHC, the example is that we are collecting the data every 25 nanoseconds. We are digitizing and
extracting.
That's the 40 megahertz is the collision rate.
Yes.
Right? So if you want to have that kind of automated data acquisition rate, it is not about like turning the knobs and I can just get it from the oscilloscope. There has to be sort of full development which has to happen.
There, and then you would be able to do that. Absolutely.
So, and the thing is that, to start as the smaller groups, we can always have it. Like, for example, the silicon detector which I talked about for the HLLSC, right? We will have like something like 25,000 modules of one type in the final detector. But I can always have a test stand, which is one module, which in fact I have in the lab here for training the students.
Nice.
Okay, so there you can learn it, like how the various things are coming in. That what the DAC part is, basically how your computer is talking to your detector and getting the
information out of that particular.
Yeah. So the starting point, that is fine. But if you want to scale it up, it needs a different level of effort.
Correct. So now that we have got a very good kind of picture of the kind of work what you have been doing, and you also have been training a lot of students who have done very well as part of their PhD and who are hopefully the next generation of scientists who are going to work on these important experiments.
Yes, they don't have a choice; they have to.
But they can also go into industry and other things.
Easily.
That's one of the good things about working in an experimental lab. you would be also employable in that sense. But in the broader context of working with the Indian PhD students, I know that a lot of students do take a lot of inspiration from you in terms of the way they want to build a career and other things. What has been your general observation within the framework of PhD students, and especially in India? What is good and what is something you would probably want them to focus a little bit more?
I think this is a difficult question for me because I somehow, when I'm talking to students, I never bothered about that they are from here or I'm talking to somebody from outside.
Yeah, true. That's true.
So, I think the initial training matter. What we lack here is the lot of exposure which the big groups might get.
Okay.
Easily outside. Right? We are still in a smaller experimental part. Like in IISER, for example, there are only 2 faculty in CMS.
Okay.
But the particle physics and experimental particle is not about just CMS.
Yes, absolutely.
There is much more going on around.
Absolutely.
Now, over the time with the Zoom and all, the online seminars and all that, it has sort of changed, but it's not same as being in that environment.
Exactly.
So I think the regular travel of the students even to CERN is important because not only they have to contribute to the experiment by doing shifts and all that, but also this exposure. There is something more going on.
Absolutely.
The other thing, I think our students somehow, I'm not sure if it is with outside or not, so I can't comment. It's not a comparative statement, but sometimes the experience was that, it's already done, why should I do it? I'm like, okay, fine, you use your part, your thinking and improve it.
Yeah.
And when they see that, they have done better than what is already published, it's a different experience and different sort of confidence which builds up.
Absolutely right. Absolutely. In fact, that is such an important part of training, right? Because that's how you start thinking about an important problem.
Yes.
You get an exposure to the topic which has already been understood to a reasonable extent. And you can also add something with your own creativity. That
can be as simple as how to present the things. How you are presenting your results, or how are you sort of simplifying the complicated business.
Absolutely.
It can be anything, right? So, good thing about sort of the Indian PhD students, the students I worked with especially, were they were all motivated.
Wonderful.
They were all sort of wanted to get into science. So, sometimes I tell them that, okay, I have to come to office because they are in office.
Yeah. No. In fact, the students, as I've been actually always telling, even as part of the podcast, the learning happens on either side, right? Because we tend to also learn and from the students, and there's a lot of learning.
Actually, I'm for example, now I'm learning more from my students' hard work than what I am actually putting in.
Yeah. No, that's something which is always we are thankful about, especially in experimental labs, and I'm sure that is the same in any other
but I think
endeavor.
What is important is the initial mentoring. That is extremely important. But the students, otherwise, I think, if they get the right exposure and right environment, they can do wonders. I don't think they are lagging behind in anything.
Absolutely, I agree with you. It's an important thing, especially if they realize that there's so much of interesting science which they can do.
They can contribute a lot.
That's true.
I think for the science part, it's not about only learning. It's also the fact that you have to contribute. You end up contributing. If you're doing your part properly, you end up contributing.
Absolutely.
You don't have to make any extra effort for that.
Exactly. You don't have to go over and above what you've already been doing.
Yes. And ours is, I call these mega science projects more of the contributory science. It's not about my paper or my this thing, right? Okay. So there is a difference in the sort of cultural aspects of it. Working in a big collaborations and other things. Yeah. I think the challenge always is that, in these big collaborations, how do you find out your own piece and be responsible for it?
Absolutely. Because there is also a bit of ownership you can have of the work, and it also gives you some...
At the same time, it is sharing also.
Exactly.
Credits are shared.
So it's a kind of a wonderful thing, right? Because it's also an important model for probably the whole world, because you really are working towards a common goal, and you're bringing people from various different cultures, backgrounds. I think that is underappreciated. In fact, that's a great model for the whole...
That's exactly what is underappreciated about these bigger projects.
Exactly.
The mega science projects.
Yes.
So for me, going to CERN even today is sort of, even though when I'm tired or something, it's mentally exciting because it's again, I'm talking to the group of people with whom I'm working towards meeting the same goal.
Absolutely.
Right? And
no, that's actually a very important thing.
Very important.
Very important thing.
So I think that's how the particle physics sort of got streamlined and organized in some sense. But that doesn't mean that everything has to go this way only. We also have these smaller experiments all across the world.
Yeah. Absolutely right. Absolutely. No, that culture, that of course particle physics has its roots from nuclear physics, and the culture of experimentation is so strong. In fact, that is one of the probably the most beautiful aspect of this sub-discipline in physics is that jugalbandi between experiments and theory is so strong,
actually,
right?
That jugalbandi is what got me excited into the science and physics, especially particle physics. Right?
Exactly. Yeah.
Because the particle physics is close interaction with the theorist and
experiments and things. No, this is something I keep also telling to my...
because initially the field was driven by the experimental observations.
Absolutely.
Then came the theory, and then again the experimental.
And
then there were some predictions which came out to be correct, and we could measure some of the new particles.
And series of Nobel Prizes. There's always, I keep telling even to my students that the competition between high energy particle physics and optics. If you see, especially in laser physics also, there's a lot of Nobel Prizes. Yeah. And generally you will also tend to see some or other things coming.
What? It's more than Nobel Prize is something different. So I read about, like, for example, this electroweak symmetry breaking and Higgs mechanism and all in my MSc. For the first time, that's when I was exposed to, right? I mean, it's just introduction. But when the Higgs was discovered, I was already in the CMS. And I was at CERN that time, actually.
Oh, when the discovery happened?
When it was announced.
Oh, wonderful, wonderful. How was it? How was that? That would have been great, exciting.
Yeah, so I could not make it to the main auditorium. It was crowded. And blocked and everything. But I was in the other room where it was transmitted.
Okay.
And it was announced anyways in the IISER conference.
Yes.
So I think even I could see like sort of those equations materializing. I don't know how Higgs would have felt.
True. That's true. In fact, Higgs himself actually has mentioned that, right? Because
I can't have imagined that how he was feeling. Because to me it was more than Nobel Prize already. It was exciting.
Yeah, exactly. It's kind of also co-participant in the whole discovery.
Unfortunately, we have not discovered anything beyond Higgs yet. So let's see. Research continues.
Yeah.
But it's also about like really sort of catching up with the new technologies and all the experimental
aspects and other things.
With all these like sort of experimental techniques, not about the detectors, but also the analysis techniques, right? All this machine learning and all. See, machine learning has been there for ages, right?
Yes.
It's nothing new that came out. It's just the computing resources have grown up so much that you can really use all these complex algorithms. And there have been developments in the like both computer science and the mathematics right?
and
which we can pull now and start employing it for our problems.
Wonderful. That's actually something which is very valuable also going further, and that's something which is very important.
So it's like sort of like is the physics part of it which we are looking after, but then there are like tools and the experimental part of it. So there's a lot of stuff going on.
Wonderful. Now we'll switch a little bit about your interests. You did mention that you read, and probably also maybe having some other hobbies. Do you have any specific hobbies?
I don't know what hobbies I have. So I was, I think from childhood I was more of an introvert person. So, but I think many things changed over the time, hobbies and all this stuff. But I think my sort of love for reading did not diminish. That did not change.
Wonderful.
So I think I was fond of reading from my childhood and grew up in a very sort of parents were quite religious and it was quite conservative family. But then the books were different kinds.
Nice.
But I think I grew up, in fact, I used to love Hindu mythology. I still love it.
Yeah. You still read them or?
Not much. I don't have that kind of patience anymore.
Okay,
But anything and everything can happen. You can choose what is possible and what is not possible. That actually helps me to appreciate okay, fine.
Yeah.
What are the realities and what are not. Absolutely. You don't have to start arguing with everyone and all.
Yes.
But you can build up your own reasoning and have a like sort of acceptance as well as the openness in it.
Absolutely. That's something which is very important.
Yeah. So no, I don't read, but I still sort of have nostalgia feeling about those times when I used to love it.
Absolutely. In fact, that is an important point, and which means that you also have a kind of a inclination towards some kind of genre of reading, including novels and other things.
Yes. So that's how I started, right? I mean, then I think whatever books were available that time, I mean, I would just love to read it. In Mahani's college, the library was quite good.
Yes.
So there, in fact, the literature section was also very rich.
Nice.
So there I end up reading a lot of books. And that's actually when I started. I think it was a mix of the things. Like earlier novels were less, but after BSc it were more. Because exposure was not there. But then I also read a lot of the sort of what generally sort of appreciated ones like Premchand and all. I think I read all his novels at some point.
Nice.
All his writings in that way. Over the time, I think I got into a little bit into the English classics, a little bit of those novels again. Some of the books, like, I don't think I can read them now, but I thoroughly enjoyed that. It was a different exposure. I think it was more exploring.
Absolutely.
Then I think I got interested in the history part of it.
Yes, nice.
So part of it, I think, thanks to, again, my PhD supervisor. He is well read.
So what kind of books you really love about these kind of genres, what you just mentioned? You have any
so it keeps changing.
I
can sort of keep switching here and there.
Okay.
Yeah. So, but at some point in time, I think I was just introduced to like some of the books by Dalrymple. And
Dalrymple, yes.
I really loved it.
There's a new book also.
So sometimes they become too thorough and this thing, but I still love those.
Yes.
But then I think just before, this was an interesting one. So just before I was moving to FermiLab as postdoc, I just went to one of the bookshops in Colaba, and there was an elderly person. Uncle, I need something for the history of India. And he was like, these are the two books I highly appreciate. I think those were excellent books.
Okay.
So there was a wonder that was India.
Wonderful that is.
Yeah. So I was talking to my PhD supervisor at that time. My ex, sort of like, he was already at FermiLab. So he was, still I was chatting with him about various projects and all, but our interaction with the non-physics stuff continued. So that time I think he introduced me to some of the books, and that's when I also got introduced to the history around World War II.
Nice.
And that's where the connection with the particle physics and nuclear physics part comes in. And that's still one of my favorites.
Wow, that's in fact.
I still do learn a lot, because when times what happens that I read but I don't remember much, because it's more of the experience. Not for remembering the things.
Yeah.
So sometimes I miss out.
Yes.
But I still love reading those parts.
Absolutely. In fact, I always keep telling. In fact, Steven Weinberg, who is a celebrated, particle physicist, who also was a Nobel laureate, he has this 4 golden lessons, very famous article I keep referring to in my podcast. And there he mentions about why reading history is so important.
It's extremely important because it doesn't give the perspective otherwise. Science as in human pursuit, like humanity.
Absolutely correct.
Sort of as a pursuit, it doesn't give otherwise.
Absolutely right. I totally endorse the point.
Not only that, I think it also helped me to understand the physics better.
No, this is precisely why I also am very interested in that, because your understanding of the physics is much richer.
Yes.
And you would also get to understand nuances of the subject more thoroughly by reading it.
And also the fact that this one statement is not one example is not the base of a completely new breakthrough of a new idea.
New idea, exactly. It's an evolution which will.
It's an evolution which goes.
Yeah, true.
That we miss out.
Yes, absolutely right. That's wonderful. That's fascinating.
Yeah, but then I think I was also reading. I'm forgetting the name of the author, but the Science in History. It's a set of 4 books. That's interesting.
Nice. Wonderful.
So it's different kinds of trying to look for the same thing, like how the societies develop. Why some communities became much more advanced as compared to others.
Yes.
It's not that the actual human evolution started somewhere. It's just the resources that were. What the requirement was.
You're right. Even if you look at the onset of agriculture, for example, it generally is around the places where there is a lot of water. And there's a human settlement close to a river, habitual aspects of it. There's some fascinating evolution happening there. Great. That is actually very interesting.
Those type of things, I think reading is, for me, it's important. Otherwise, I won't survive.
Yeah. No. It's something, as scientists, that constant renewal is very, very crucial.
Actually, So I think at times it was also for me run away from all the sort of problems of that point. I'm reading, I'm away from it.
Yeah, you're right.
So that sort of helped me to calm down
and relax, and that's something which is very crucial. And especially people who are deeply involved in some work, they need a let out of some kind, which is very necessary. That's a crucial element of it. So,
other than that, I used to try whatever. Small things here and there. After COVID, I'm cooking for myself, so even that becomes experimental for me.
That's good. That's very nice.
Okay.
Nice. So one of the things what we do in the podcast, especially with the guests, is also I request them to just speak a few kind of sentences regarding their work in their mother tongue. So I would request you to just kind of tell our listeners a little bit about your work and your motivations in your mother tongue. And this is a trend we have in the podcast, and it would be nice to have your input in that.
तो बचपन से लेके कॉलेज से लेके यूनिवर्सिटी से लेके पीएचडी और अब यहाँ पे फैकल्टी सारी बातें की है, राइट. मतलब मुझे अब तक जितना समझ में आया, विज्ञान भी एक जीने का तरीका है. यू हैव टू लाइक सॉर्ट ऑफ अपने रीजनिंग डेवलप करो, अपने लॉजिक डेवलप करो. ये नहीं है कि हर किसी को जाकर के एक्सपेरिमेंट ही करना है लैब में. ऐसा भी नहीं है कि जाकर के इंस्ट्रूमेंट के नॉब्स लाइक चेंज करना है, बटन घुमाना है, ऐसा कुछ नहीं है, राइट. तो हमारी रीजनिंग जो डेवलप होती है ओवर द टाइम, वक्त के साथ में, पढ़ने के साथ में, आई थिंक वो लाइफ के हर एरिया में नजर आती है. अगर तुम कभी फाइनेंशियल प्रॉब्लम भी आ जाओ ना, तो भी नजर आएगी वो किसको कैसे बाहर आते हो उससे. ओके, सो सबसे ज़्यादा इम्पॉर्टेंट है जबकि हम लोग ग्रो कर रहे हैं, बड़े हो रहे हैं, जिज्ञासा, ओके, एंड रीडिंग. ये दोनों चीज़ें बहुत ज़्यादा ज़रूरी है.
बहुत इम्पोर्टेंट. सही है.
ओके, जिज्ञासा का मतलब ये नहीं कि हर को जाकर कि घर पे एक टीवी सेट है उसको पूरा खोल करके इतना ही करना है कि उसको वापस में जोड़ पाओ. जिज्ञासा का मतलब ये नहीं कि चीज़ें बर्बाद करनी है. जिज्ञासा मतलब ये है कि जो कर रहे हैं उस पर एक बार ध्यान तो दो और वहाँ से तुम्हें मिल जाएगा लिंक कि आगे क्या करना है. तो बाकी जैसे जैसे बड़े होते हैं, साइंस में रहते हैं, तो हम लोग अपने रिसर्च प्रॉब्लम्स ढूंढ लेते हैं, किस पे शोध करना है, किस चीज़ पे फोकस करना है, वो अपने आप आएंगे धीरे धीरे. तो मेरा जो काम है वो पार्टिकल फिजिक्स में है. ट्राइंग टू अंडरस्टैंड कि एलिमेंट्री पार्टिकल्स क्या होते हैं. एलिमेंट्री पार्टिकल्स का मतलब कि उनका कोई मतलब आंतरिक स्ट्रक्चर और नहीं है, लाइक कोई पॉइंट पार्टिकल की तरह. तो अभी रिसर्च उसी में जारी है.
Wonderful. Thank you very much, Seema. That was wonderful because see, this is a kind of deliberate effort. Why I'm trying to make people speak in their mother tongue, because that is a very crucial factor in motivating.
I understand.
That is an important thing.
That's what I said. No, that in the initial education that was very important factor for me. At this point, doesn't matter.
It doesn't matter. Yeah, exactly. See, once you are at a different stage, maybe you will not be able to kind of put emphasis on that. But while growing up, it makes a lot of difference. Yeah, because if there is a potential listener,
actually, yeah. So it might be that now how the things have changed, I don't know. What I am saying is that from my experience, 30 years ago, that was important.
Yes, absolutely right.
Now, I mean, if the parents of my age group, they are all like sort of equal with English, then probably it doesn't matter to them. So we also have to grow up.
Absolutely.
According to what the requirement of the time is.
No, this is something which is very crucial, very, very kind of in-depth kind of stuff. What is required for one to become a scientist? It needs effort from every
the language should not be a barrier.
Exactly. True.
So actually, the first time I started speaking English was only in TIFR.
Yeah.
Before that, we had the writing in English. The question papers were in English.
Yes.
Teaching in MSc was also in English, partly, sometimes English. But the actual me speaking happened only later.
Wonderful. That's something which is very crucial. So now that we are almost coming towards the conclusion, what are the kind of areas you would be looking forward to in terms of your research? What new kind of directions you would prefer to see the field go towards, and in what direction you would actually want to proceed? Could you just tell us a few sentences about that?
So there are again the two aspects of it, right? That one is that we have to, as an experimentalist, as a particle physics experimentalist, my responsibility is also to churn the data. In all possible ways. You cannot really leave out even a small physics space.
Absolutely.
So what I would like to go for, change a little bit my direction and maybe look for go towards more Higgs sector or the top sector and try to combine the measurements, precision measurements and the new physics searches.
So because the dark matter question is still unanswered.
It's still there, but there can be variety of ways one can answer that. So we have to see. So until now what I was doing was really looking for the high, sort of very large missing transverse momentum that some dark matter particle produced and just went away.
Okay.
Now I can try to look for maybe more particles which are visible in the detector. For example, the soft probes, where the momentum is very less. So your signature in the detector is small, but then you have to overcome a large background to make sense of it.
To make sense of that particular thing.
So that is something which I would like to go for. I mean, exploring with some of the master's students.
Nice.
Pseudoscalars, like Higgs, becoming to pseudoscalars and trying to see. And you know what? Even though I think there is a lot which I don't know, and that is the fun.
Absolutely.
Simple things which we are just habitual of, how they behave in a different momentum regime. comes out anytime.
In fact, I generally tell,
So-
in the podcast also I emphasize that a professor is a student for life.
Yes,
That
it's
sense.
a commitment to be a student for life. That's what I'm realizing with my every next master's student, I realize that.
Yes.
And the other aspect is essentially I told you that I would like to continue some involvement in the detector physics part.
Okay.
Not some involvement, but a big chunk of involvement because that is the future and that's I enjoy. And that's important for the students to be able to appreciate the experiments.
Nice.
So that's something I keep trying on and off. Let's see.
Wonderful.
It depends on how the students come up and I hope they stay interested in both the aspects.
Yes,
Then it's fun.
yes. Yeah, you also do a bit of outreach activities, right? You do actually do some kind of outreach for the CMS also?
Yes, so it's not like sort of formal assigned or any commitment that way, but I like to and love to interact with the students, the younger ones.
Yeah.
And for that, I do give whenever there is an opportunity to talk to them.
And that's a crucial factor of building a good community in terms of...
And also I have come, I think I can now look back and see, like, it's not like immediately as a joining faculty that is still not away from my own experiences of being young. So I think now I can talk more freely about like why they are getting, what their fears are.
And things. Nice. Very
But
nice.
yeah, I just sort of love to interact with those students.
Those students also.
So I think my outreach has been more about that one, but not any like very large scale kind of it.
Yeah, because I know within our department, so many students do come and consult you and get your input.
Yes,
and
that
other
is
things.
always there.
That's something which is very important.
Yeah. So for the students, I think most of them know it that they are welcome to come anytime for whatever they want to talk about.
Absolutely right.
That
Absolutely.
is an open
Invitation. Always.
invitation.
Always. Great.
Whether they are working with me, not working with me, whatever topic they want to talk about. I don't mind listening to them.
Yeah. No, I know.
Sometimes what happens is that they just need like
Some kind of a channel. Some channel to
sort of like. And sometimes you know what, you don't have to say anything. They just figure out their ways.
Yes. No, I kind of totally see the point what you're making. Great. This has been a great conversation. I thank you very much for your time.
Well,
and also,
for the opportunity.
Then there are a lot of things to revisit and kind of think a little bit more about what you've been kind of telling. And hopefully the listeners will also be able to kind of grasp many of the concepts. And ultimately, the motivation behind Pratidhwani is to humanize science. So
Yes,
in that sense,
I think that's important.
That's a crucial factor what we are looking towards. So thank you again, Seema.
Thank you.
Thank you very much.